From the moment we wake up until we fall asleep, we use our muscles to perform everyday tasks. In skeletal muscles, these movements are caused by electrochemical activities collectively referred to as excitation-contraction coupling. During a voluntary muscle contraction, neurons from the motor cortex send signals to the anterior horn cell via the corticospinal tract. The anterior horn cell depolarizes, and an action potential is propagated through the axon. Voltage-gated calcium channels of the terminal button open up and allow influx of calcium ions. A rise in the intracytoplasmic calcium triggers exocytosis of the acetylcholine-containing vesicles. Acetylcholine traverses the synaptic cleft and stimulates the nicotinic receptors, leading to an influx of sodium ions. Influx of sodium depolarizes the membrane potential. Once this membrane potential reaches threshold potential, an action potential is generated in the postsynaptic cell. The action potential travels along the sarcolemma down the T-tubule. Depolarization of the T-tubule causes a conformational change in the dihydropyridine voltage centers, which in turn causes the opening of the ryanodine channels, allowing the influx of calcium from the sarcoplasmic reticulum to the myoplasm. Calcium in the myoplasm binds with troponin C to inhibit the troponin-tropomyosin complex, thus uncovering the actin-active sites. When the actin-active sites are uncovered, the myosin heads attach to it and a power stroke occurs. Muscle contraction is thus achieved. Muscle relaxation. Cross-bridge cycling stops when myoplasmic calcium concentration goes down to a critical level by the influx of calcium from the myoplasm into the sarcoplasmic reticulum via the calcium-magnesium ATPase pump. Generation of the action potential stops when acetylcholine concentration along the myoneural junction decreases through pumping back of acetylcholine into the axon end and degradation of acetylcholine by acetylcholinesterase. The absence of acetylcholine along the myoneural junction will mean the absence of action potential propagation to the postsynaptic cell. The lack of action potential tends to keep the ryanodine channels closed, thus calcium cannot flow into the myoplasm. No calcium along the myoplasm means no cross-bridging. Affectation of the cerebral cortex in cases like cerebral vascular disease causes paralysis of the contralateral side of the body because the presence of an infarct blocks the transmission of impulses from the motor cortex to the anterior horn cell. Transection of the corticospinal tract in spinal cord injuries causes paralysis below the level of the lesion because the signal from the motor cortex of the cerebral hemisphere cannot be transmitted to the anterior horn cell. Affectation of the motor unit can occur in the following segments. First, on the anterior horn cell. Destruction of the anterior horn cell in cases such as poliomyelitis leads to paralysis because the action potential cannot be transmitted from the cortex to the axon. Second, decreased acetylcholine receptors in the postsynaptic cell in cases like myasthenia gravis prevents the generation of an action potential in the postsynaptic cell. Lastly, electrolyte imbalance in the muscle, such as hypokalemia, causes muscle weakness because this phenomenon tends to favor potassium efflux, making the cell more positive, thus preventing sodium influx to allow depolarization. In summary, skeletal muscle excitation-contraction coupling happens via the following. The action potential travels through the motor axon terminals. The influx of calcium. The release of acetylcholine into the myoneural junction. Nicotinic receptor stimulation at the postsynaptic cell. The influx of sodium. The depolarization of the T-tubules. Dihydropyridine stimulation. Ryanodine channel opening. And calcium released into the myoplasm. Relaxation occurs when acetylcholine is degraded by acetylcholinesterase and is pumped back into the presynaptic terminal. Therefore, action potential generation stops. Muscle weakness may be caused by a cerebral cortex infarct, a spinal cord injury, the destruction of the anterior horn cell, decreased acetylcholine concentration and acetylcholine receptors, and lastly, by hypokalemia.